Okay, so far if we look at the last part that we did last time, it's about we did a couple of examples of the problem of the fundamental theorem of calculus. So let's do some more of the fundamental theorem calculus problems and then continue uh, with the material. Okay, with this session 11.1. So recall that what we had last time. Computing function written in terms of integrals. And so this is what we did. Okay, mostly that kind of problems that we did last time. Okay, so this is the finding the intervals of for the functions be increasing, decreasing, okay, up and down. Okay, so based on derivatives. So again, you taking derivative of functions in terms of integrals. All right, so let's continue with some more example. All right. There's problems. Questions. Okay. Second. All right, so let's do some of the problem in 12 example. Okay, so first of all, I remind you again about what we will use our substitution method. You recall that the substitution method as opposed to as an inverse to product rule. Okay. Product rule, chain rule, sorry. Recall that if we have a compositions and you take the derivative, that chain rule. So this is we have derivative of f computed at g of x. You multiply by g prime of x, derivative of what's inside. Okay. So if you use antiderivative, then you have that means you have that plus c. So you won't get exactly this, but plus c. But it's this is what we call a so this method f prime over g of x times g x. All right, so in here let u equals g of x. And now recall that we define a differentials, so differentials of u that equals g prime of x times dx. Okay, so this is exactly, this is our dx, du. Okay, this is our u. All right, so this is f prime of u du. Okay, so this should supposed to be f of u plus c, which is f of, and substitutes back Okay, so this is called substitution method. Okay, so the key is in choosing choosing the proper one, right? So somehow you get to find u so that the derivative also appears in the integrals. Okay? So that's what we call substitution method. Okay, so the second fundamental theorem of calculus says that if you compute uh, a, a definite integral, what you need to do first is to compute antiderivative and then uh, compute the difference. Okay. Okay. So let's do this one. For example, let's problem A. I do problem B instead. Okay, B and C. Okay, so let's see. Okay, so let's for B. Okay, so integral 0 1 x squared plus 1. Oh, so that's the idea. How would you choose? Uh, how would you choose a u here? Substitution method. So we let u equals. So in this case, u prime should be uh, part of the integral. Okay. So see here. Here we have x squared plus 1. Okay. If we choose x squared plus 1, then the derivative 2x should be here, but this is just 2x exactly. Okay, so we choose u is that one. Then du equals 2x plus 1 dx. Sorry, 2x. That's exactly. Okay. So by substitutions, we get uh, okay. Now what I like to do here is that if you write this down as a u, this becomes du. You should write down the bound as right. So this is actually x. I write this down uh, just to make sure that you observe the bounds. variables, okay, the variables of the bound, this x. But here, because you would like to integrate in terms of u, this should be u, okay? And while you're doing this, you compute also the bound. If x equals 1, then u equals, because the u is x squared plus 1, so we compute this. 1, so 2. X is 0, u is 1. So now the bounds become from 1 to 8. Now we compute this one. We're looking for a antiderivative. We call that the formula for antiderivative. Okay, so this will get you to increase the power, okay, and then divide by the new power. That's 1. Okay, you may add plus c, but c will cancel anyway if you compute the difference. Okay, c will cancel because you compute. All right, so this notation is difference. Okay, so you compute, so 1/10. So you plug in 2, okay, then plug in 1 plus c, right? And then you subtract c. So c will cancel anyway, so you don't need to write it down. Okay, so that's how you get the number. Okay, and this by FTC, the Theorem calculus, second. All right, or problem C. Okay, see that the thing is, seems like we have a two choices for u, right? X squared, or we choose this x cubed, or x cubed plus 2. Okay. All right. If you choose the x squared, let me write this down. Then we have du equals to x. Okay. But what we have so far is, well, this doesn't work because what we have is this one. Okay. So it seems disconnected from what we have here. So that's. You see the reason? Are you with me up to this point?
Yes, sir.
Okay. All right. So then it's not a good choice. Not a. It might work, but at least it will take you quite a long while. Now we choose u equals x cubed. How do we work now? Because it is cubed, then the derivative is square. Then we have this x squared. So we have this 3x squared, so you just take 1/3 out. Okay. All right. So when you do substitutions, we have this substitution, I would say, substitution method. You have this 1/3. You take 1/3 out. Okay. And this is just u. This is just a u to the fourth. Okay. Recall that we have to compute also the bounds. If x equals -1, then u equals, let's see, this is -1 plus 2, this is not 1. X equals 3. Okay, 3 cubes, 27 plus 8, 29. Okay, so we put this back. Q equals 1. There. So that's one thing that you need to remember. If you do the integral in terms of u, then the what do you call it? The bound for the lower bound and upper bound for the integral should be using the same variables. Okay, so let's compute this one. There is basically integral u to the 4 -4, right? There, 1/3. Now this is using fundamental theorem of calculus 2. Okay, so raise the power by 1, so u to the -3 now, because you add 1, and then divide by this -3. Okay, so you have, okay, so do this one. Let's see, what is this? Sorry. One over -3. Okay, so 1/9. Cube. Okay, so that's the number. Okay, so that's how you do this kind of problems. Questions?
Sir, I have a question.
Uh-huh. Sure.
Where did you get the x equals to -1? Did you just pick an arbitrary number?
Which one? This one? Here.
Oh, okay. Sorry, sir. Okay, thank you, sir.
Okay. Let's see. All right. And okay, let's go back down to the let's do okay, I'll pick one from okay. Now that the sorry, I okay. All right. Okay, so a little bit, sorry. Okay, I think that works again. Okay, share the screen. Okay. Yes. Substitutions. There is. Oh, okay. So let's miss that one. That's the from the previous sections. This is substitutions. Let's do more of this. All right. Now let's do, for example, it's easy one. Okay, let's do, for example, this one here, 44. Okay. All right. So we have here these two choices. Would you choose cosine or sine here? Okay. Uh, we choose this one. This one, the both might works. Okay, let's let you be, for example, if you choose cosine. Yes. Okay, then du is cosine, the residual cosine, and negative sign, right? So negative 3 sine 3x dx. Okay. Uh, but the thing here is that the what we have here is that this is a sine square instead of just sine. Okay, so we don't have this one. Okay, so we don't have things to match this sine square. So you should have square of this. But if you square this, then you have du square. You don't have such a thing. Okay, so this won't work. It's not good. Okay, so the only choice that works. Let's see the with sine. That if you choose sine, then we have 3 cosine 3x dx. That's exactly what we have here. Just 1/3. Okay, so what you have here is that, oh yeah, we need to compute also. If x equals 0, then u equals sine 0, just still 0. x equals pi over 2. So u equals sine 3 pi over 2. 3 pi over 2. That is -1. Okay. So after substitutions, we should have, right? So that's the bound. The integral, this becomes u squared. This becomes 1/3 dx. So we take 1/3 out. Okay. And this is by fundamental theorem of calculus. We should have a derivative of u square, antiderivative, q, so, okay, and you compute at 0 and -1. So you have 1/9 cube, plug in 0, -1. Okay. Plug -1, you get, just take 1/9 out. Okay. Okay. Questions? Okay, so I just pick up a problem and you tell me now, what should be used as a u? For example, this one. How we choose u? It is the sine or the cosine as u.
Is it the user? What we're trying to find the U, right?
Yeah, yep. What you should choose for u? Is it the sine or the cosine?
Is it the cosine, sir?
A cosine, right? Because the derivative is sine exactly as so the top you have sine. Okay. If you choose u to be sine, that's true. Is you have the cosine, right? But the thing is, you have u, you have cube there, cosine, right? So not exactly cosine, but you cosine cube, and it won't work because then you need to have a cube of du. That's not good. Okay, so choose u equals here. Okay, so that is du is negative sine dx, or d theta in this case. Sorry, it should be theta. Yeah. Okay. That's this example. Okay, so I'll let you do the exercise later. All right, so let's do some more problems. For example, this one here. So compute this limit. This is the type of problems. For example, let's pick problem 70. limit. Um, okay. So the thing is, if you read this, the problem, let's go back to the problem. So, see the instruction here. It says, first recognize the given limit as a definite integral. Okay. Then evaluate the integral by second fundamental theorem of calculus. So let's take this writing this limit as a definite integral, meaning that you should recognize this as a Riemann sum. Okay. That's, so first you have to recognize sigma as Riemann sum. Riemann sum, that means there, sample, and then, okay. So here what you need to recognize is what is, take this limit, as the partitions to 0, just give you, okay. So recognizing the sigma as a Riemann sum, that means you try to find f and b. So we need to write this down as an integral. Okay. All right. So let's see. From this problem, this tells you that this one should be the delta. All right. So this is the, how you call it? Yeah, this delta. So but the thing is, so what is this? Okay, so this supposedly f of x. Okay, so in this case, the counter, I mean the index that puts is the I start from 1 to n. Okay, so I equals 1, that is 2 over n. Yes, right, 1 over 1. So 2 over n equals to 4 over n. There, and 2n over n, which is 2. All right, so we know from here that we are dividing the interval from 0 to 2 into n equal parts. Just partitioning. To n equal parts, equal length. Okay, so what we have is this. To 2. Dot, dot, dot. Okay, so this is 2 over n, 4 over n, 6 over n. Okay, so let's match up with this plot. Okay, so from here we can make a guess that the f of x should be this is x0, x1, x2, 3. Okay, so that means this 2I over n cube, because that's cube. That should be f of x. So then the representative is just 2n over. Okay, and the function should be s cube. Okay, so this is just a series of kind of systematic guessing. Actually, you're guessing what A and B just from the way it partitioned. Okay, so find the f. So all right. So when we get this, we realize this limit as a integral from 0 to 2 cube dx. Okay, which is raised to the power of 4, 1 plus 3. Okay, FTC, right? So plug in 0 and 2. 2, 2, 4, 4, 16. Yeah. So you get it. Okay, so the important thing is this one. Okay, questions? All right, so let's do go back to, okay. Let's just do some scratching here. First of all, this one here. Okay, so what is delta? You didn't have much choice in choosing delta, right? It is supposed to be delta. Okay, so you like from this form, you like dividing pi, right? 0 to pi into n equal parts. Okay, so n, so 2 pi over n, dot, dot, dot. Okay. So from here, we recognize this is, okay, so this is exactly sine 9. So what's the functions? What is f in this case? So this tells you this is A, this is B. Okay. What is f then?
Is it sine x?
Just sine x, the sine. Okay. So this is just the limit of Riemann sum of in the integral 0 to pi sine x dx. So this tells you yeah. Okay. Okay, let me just move this to our notes. Okay, so that's all right. So let's take a break for for a short, maybe just 5 minutes. I need to read but your schedule. Okay, let's take a break. It will be back in 8 or 6 or 8 or 7. So I will pause.